So every single element on the periodic table, we're going to end up with a series of 4 numbers called the N, L, M, and S numbers. So it's kind of like a street address, how you have like on an envelope you have your state, your city, your street, and then your like house number or fire number or what have you. So that's just going to kind of act like for elements. So quantum numbers are the address of that outermost electron. Every single element has a unique pattern of electrons, so each one's going to have a unique quantum number. So the first one, the N value. This is called the principal quantum number. And the word I want you to have associated with this, the N value is synonymous with the shell. So I'll say that the shell that it's located in. So like in those pictures of atoms, we looked at that Bohr atom yesterday, you got those rings that represent the different shells. That's what the principal quantum number is going to tell us, what shell it's located in. When we assign the number, it's the row or the period on the periodic table. For most things on there. For our transition metals, it's going to be the row number minus 1. For the rare earths, it's going to be the row number minus 2. So each element's going to get assigned 4 of these numbers. We're going to go one by one. So get out this blank periodic table. And the first thing I want you to do is you're going to draw a box right up here. And then you're going to go over across the periodic table, and we're going to take where helium normally is, and we're going to cross that out. We're essentially moving helium over here for the purposes of assigning quantum numbers. Okay, so again, the convention is for N values, N is equal to the row number. So we're in the first row, or the first period, so it's 1. We go in the second row, and it's 2, but that second row continues across the periodic table over here. So I'll put a 2 in all those spots. Move down to the next period, 3. That period goes across that gap in the table. And you continue. We drop down to period 4, but then we run into the transition metals here. So the N value for all of our transition metals is going to be its row number minus 1. So it's going to be 3 in here. Then we exit the transition metal block, and it goes back up to 4 again. And we repeat that pattern. Row 5, and then we drop the transition metal block, so then we go down to 4 and minus 1. And then back up again. Drop down to the 6th period. And then we run in these little little hash marks here. What does that indicate? You guys remember what that signifies? That's right. That's where the rare earth metals go. So these two rows down here actually slide up into there. So they belong in period 6 and 7. So for the rare earths, the N value is row number minus 2. So this number is going to be 4. And then we hop back out, back into the D block up here, not D block, the transition metal block. And it'll be 5. Yeah. What I'm hoping you will see throughout the day today is there's a very distinct pattern to this, how all of these get put on here. Okay, then we drop down again in the 7th period. And back into our rare earths, so 5s. You're eventually going to have 4 numbers in all these little boxes here. The rare earth will put 3 numbers in, but I'll show you how to manage that. Okay, you can put this off the side. We'll talk about the next number. Our next one is the L quantum number. And the L, what this is the shape of the orbital. I'll explain what an orbital is in a bit here. The term I want you to know associated with this is subshell. So shells are broken up into subshells, just like your address, state of Wisconsin, city of Portage. Okay, using that geography metaphor. The bigger the number, the more complex it becomes. There's going to be 4 of them. L equals 0. The shape of it is going to look like this. It's going to be a sphere. So the subshell is shaped spherically. That's a spherical shape. Where we're going to find this is with groups 1 and 2. So its outer electron is going to be found in this L equals 0 or this spherical shaped orbital. Really what these orbitals are is their probabilities of where this electron is going to be located. So with a sphere, it's got an equal probability of being anywhere in that area. The next one is L equals 1. And this one's shape is going to be figure 8 shaped or hourglass shaped, but 3-dimensional. Think of like 2 cue balls up on top of each other. Where you're going to see this is groups 3 through 8. They're going to be found in these hourglass shaped orbitals. So there's going to be a greater probability that's going to be in these like round areas than where they pinch off towards the center. Next one, L equals 2. And going to draw my little figure 8 shape again, but then around it, I'm going to draw a donut. So you want to picture this in 3 dimensions. Imagine a donut wrapped around an hourglass. And that's the shape of this orbital. So that's where the probabilities of existence are going to be, either in that hourglass shape or in that donut-shaped area around it, but not in the empty space in between. This is your transition metals. And then lastly, L equals 3. This is too hard to draw. It's just really complex. I can show you guys some images later on. But it's just such an increased complexity, it's really difficult to draw for our notes. And this is going to be our rare earths. So you guys can kind of see we're divvying up the periodic table into regions. Okay, let's go back to the periodic table. So, for all of our elements with groups that are groups 1 and 2, our L value is going to be 0. So L is going to be equal to 0. Then we're going to move across the periodic table to where groups 3 through 8 are located. All of those are going to have an L value of 1. Go into the transition metal area, and those are all going to be 2 now. And then lastly, our rare earths, these will all have a 3 as a second number. Okay. So we're halfway through. We got the 2 first, we're kind of narrowing down that location of that final electron. As we go through each step, each box is going to become more and more unique from the ones that surround it. Okay. Next value. M. This is called the magnetic quantum number. What I want you to remember about this these are called the orbitals. So we have shell, subshell, orbital. What these tell us is the orientation of the electron in the subshell. So where it's sitting inside that subshell. here's how we assign the numbers. They're going to range from negative L to positive L. So we have to look at that L quantum number to figure out what our M value is. So for example, if L has a value of 1, our M values range from negative 1 to 1. So negative 1, 0, 1. So you have to use, go through the full number line. Negative 1, 0, 1. All right, let's go back to the periodic table. So, again, the relationship is negative L to positive L. 0, there really isn't a negative 0 and positive 0, so it's just 0. Okay, then we jump over to where we've got L equals 1, and we're going to go negative 1 to 1. So we'll go negative 1, 0, 1, and then negative 1, 0, 1. It repeats itself. And it does that all the way through where L equals 1. Okay, let's move to the transition metals where L is equal to 2. The same pattern is going to hold. You're going to go negative L to positive L, so it's going to start at negative 2 and then go up to positive 2. So negative 2, negative 1, 0, 1, 2. Negative 2, negative 1, 0, 1, 2. And then finally, you drop down into the rare earths. Same pattern is going to hold again. Negative L to positive L. L is equal to 3, so it goes negative 3, negative 2, negative 1, 0, 1, 2, 3. So again, with the address analogy, we've gone like city, state, and street. If you want to think like, how we have negative, we go range negative to positive. You know how like on streets you can have like east and west version of a street? Think of that, those negative and positive values being that, like, oh, it's East Albert and West Albert Street. Just as an example. To give a little geographic spin. So we're almost done. Notice that we're slowly on. We're getting these numbers more and more unique, right? They're starting to look different, more and more different from all the other ones around them. Okay, last number. The last value we call the S quantum number, and it's the spin number. And what this does, it gives the direction of the electron spin. So this is a little confusing because electrons technically don't spin. All this is showing is that it has an equal but opposite characteristic. So this is some kind of characteristic about electrons that we can't really define at the scale that we live. It's not like one spinning clockwise, one spinning counterclockwise. It's a equal but opposite characteristic that we can't like really can't really give a definition to. Does that kind of make sense? So they can either be negative 1/2, which we call downspin, or positive 1/2, which is called upspin. And here's how we assign them. So the first half of each subshell, or L value, is negative, and the second half is positive. So the first half of each subshell is negative, and the second is positive. I just put quotes there to kind of speed up my writing process there. Okay, let's go ahead and put those values on our table. It's going to get a little crowded now. So we have our S value in here. So we go whenever you have your L values, just split it right in half. The first half is negative 1/2. The second half is positive 1/2. Where this comes about is that each orbital fits 2 electrons in it, but you have to fill all the orbitals with at least 1 electron before you can add a second one. So that's what's going on here. And you'll be able to see it in this section. So the first half is negative. So put an electron into each of the different orbitals, the negative 1, 0, 1 orbital. And now, once those ones each have 1 electron in, we can add a second electron that has equal but opposite spin into it. And notice now, these are all becoming unique boxes. There's no other one that looks exactly like it. What you may notice is that most of the greatest similarity comes in the columns, right? Remember that relationship, things in the same group have the same characteristics. We're seeing that with the quantum numbers too. Okay, now that I made you do it really tedious, I'll show you the shortcut way of putting those in. First half negative, second half positive. First half negative, second half positive. The reason why I have you initially put them in one at a time, it's like how we're filling the shells with electrons. We're adding electrons with each step. Filling in all of our orbitals with at least 1 electron, and now we're adding a second electron to each orbital. And since we really kind of ran out of room with our rare earths, we can just put it down below. Negative 1/2, and then the positive 1/2. Downspin, upspin electron.
Could you slide it over for the transition metals?
Yeah. That better?
Yep.
Okay. Again, every single element on here now, unique address for its final electron. Since all elements have a different number of electrons, they all have a different location for that final electron. So, for example, boron is in the upper left-hand corner of your periodic table, located right here. What's boron's N value? 2. What's boron's L value? Its M value. And then its S value or spin value, -1/2. Each of those is unique. So, do you guys want to know a little trick? Are you guys picking up on the pattern this a little bit? Starting to see it? Do you guys want to see a trick on how to fill these things out really quickly without having to memorize every single box? Okay, let me show you. What I want you guys to remember is this. 1, 2, 3, 4. 0, 1, 2, 3. I actually had another former student come up with this. They showed me this how they remembered how to fill these in. By remembering that, what you have is the upper left-hand corner of every region of the periodic table. 1/0, 2/1, 3/2, and then 4/3. And then all the numbers build off of those, right? The N value just goes up as you go down. And that happens in all those cases. And then the L value stays the same, and we build off our M value from that. So like you look in here, like 3, 2, we build up on the N value, 3, 4, 5. The L value is the same through the whole block there, and then we build our M values off that, -L to +L. And the other thing you have to remember is that M is -L to +L, and the first half is negative and the second half is positive. So I thought that was a really good tip. So I know that when they got to their test, I saw them do this. The first thing they did when they got their test out is they would go, and they would just build off of that. They'd build off those 4 corners. Okay, so that's quantum numbers right there.